everyone. So my name is Shungu Garaba, and I'm a guest of Professor Dr. Kiduru. And so today I'll try to give you some introduction on oceanic instrumentation, and we'll see how far we can go. So just a bit about my background. So I did my bachelor's degree at the University of Jacobs University of Bremen in Germany, and then that was in geosciences and astrophysics, more concentrating on the ocean. And after that I went to the University of China, where I did marine sciences, followed by another master's degree at the University of Bremen in Germany again. And the final highest degree you can get, which is a PhD, I did that at the University of Oldenburg, and I'll try to show you some pictures where you get an idea where Oldenburg is and where Bremen is in Germany. And just to show you some of the history and what has happened over the years. Some pictures, as you can see here at the bottom right, this is me doing some field work in the Antarctic area, and then the picture in the middle where I just defended my master thesis at the University of Bremen, and of course the highest degree, which is a PhD at the University of Oldenburg. And it is more of a tradition in Germany when you finish your PhD, the team or the group you are working in, they make you a nice hat, which is a combination of the things you have been doing during your PhD. So as you can see here on top of my head, there is three gun looking like instrumentation, which I'll try to explain in the coming days. And also different colors you can see on the hat. And then of course, if you have your family around, they will bring you some gifts. And as always, you have to dress nicely for the occasion during the presentation. That's up to you. Okay, so over the years I've done some teaching, and to summarize my teaching interest, so it has been mostly for bachelor and master students. So they are either courses or elective classes, and my background is in remote sensing. So we have covered how applications of remote sensing can be utilized in monitoring the aquatic or terrestrial environment, how observations can help decision making, water quality managers. So the information you get from remote sensing, how it can be used to help support the decisions made by managers, or be it policymakers. And then of course you have oil spills, you have plastic pollution, so disaster assessment, and then of course the basic science on ocean optics. And then you also have the niche of water quality, which is the tools you use for monitoring technologies, and what different agencies, international or local monitoring agencies, how they can be supported by different instrumentation, that is scientific instrumentation. And then of course, some of you might have heard of the United Nations Sustainable Development Goals. So that is in 2030, they hope to reach certain good environmental scenarios by reducing pollution and helping to improve the quality of water. And I've been also working on plastic litter or debris. So in terms of monitoring strategies, how to monitor plastic pollution, how we can also contribute to the decision making, how the cleanup activities, and also policy making. And also, when you're doing science, you have to use certain software. So I have some skills in training people on how to visualize data, once you collect your data, how to look at it, how to present it, and then also quality control, the statistics you have to use, the metrics, if you have to calculate the mean, the average, the different metrics that people utilize in everyday science. and also how to handle your data, how to make it open access so that other scientists can also have access to your data when you have collected it. And then, of course, referencing literature. So I'm also teaching a class on scientific publishing, reporting scientific data, how to do a literature review, the referencing skills, how to avoid plagiarism. So one challenge you always find in science is plagiarism. Like for some people, of course, it's not your fault. You don't know how to properly reference things, but then it's one of those skills people have to be taught on how to make sure you're not copy pasting. Was one thing I'll tell you, and I'll repeat this, like plagiarism, copy paste is, it's close to suicide in terms of career if you want to be a scientist. And then, of course, when you submit your manuscript for scientific publications, there are ways how you respond to reviewers. Well, reviewers are not paid to do the job. They are basically scientists who are interested in making the field grow and advance in science. So they are doing this out of their free time. So you have to be polite when you respond to them, and also like how to make sure you have responded to their questions. And then, of course, again, open access and the fair policy, including ocean best practices. So just a quick run through like what I have done over the years. So my work has mostly been on the ocean, and well, I tried to put this, summarize this in a few pictures. Here is one of the ships which is owned by the German scientific community. And one of the ships is called Meteor, and on our last cruise we traveled from Namibia to Las Palmas. And as you can see on the ship, it's quite big. You have containers where people bring in their instrumentation, and because of the waves and bad weather, sometimes instruments can move. So here you see we have to tie, in most cases all the instruments have to be tied down. So here you can see we have a spectrophotometer, and it is tied down on both ends, and this makes sure, you know, like when the ship is moving left, right, forward, backwards, your instrumentation does not move or it's not damaged. And of course, you see here there are cranes to pick up, you know, like the containers to put instrumentation on board and also remove it after a cruise. And one interesting thing, this is one of the sea creatures we collected when we did some water sampling. I leave this to the biologists to describe what it is, but it's quite interesting. As you can see, it's transparent, you can see through it. So this is some of the interesting things you meet along the way. And just, yeah, I don't know how you can get an impression of how big this ship is, but it's quite a big ship, and this is dedicated to science. So nothing commercial, nothing what, it's just science. So it's dedicated to doing science only. And again, yeah, I like the picture of the creature, so you see it again. So the other research I've done, I've been to Antarctica, and well, it's always, you know, it's nice to be in different places, very cold. I'm from Zimbabwe, so you can imagine the differences in temperatures when it's very hot, and then you have very cold temperatures. Here you have penguins. Then you see like floating ice, very huge, like it's difficult to even like comprehend how big this is. And then you have seals. And so when we did this research, we went to the Palmer Station, which belongs to the United States. So the Antarctic program, they have a Palmer Station in Antarctica. And let's see. So yeah, it's always difficult to like explain how big something is. So this is their icebreaker. So the icebreaker is also dedicated only for science. It's meant to travel through ice. So in some cases where the ship is traveling through ice, you have to go back and forward trying to break the ice, then you can go forward. So 70 meters long, and then you have, yeah. Okay, so okay. Okay, yeah. Is that better? Yeah, that's always duplicate slideshow. Is it better? Is it better? Is it okay? Yeah, okay. Yeah, so, yeah, so on the Lorraine Good, you can go out at sea for 75 days. So for the experiment we traveled on, we spent 45 days, but then here you have 26 scientists, and most of the research on this ship is in the Antarctica area. And sometimes, of course, if they have to do some services on the ship, it has to travel all the way up to the USA. Yeah, just a bit more of the impression of like what you'll be seeing every day. You have big, very huge like ice caps, and then you have, of course, the lazy seals, they're just sleeping there. And yeah, so this is an image of, let's see if I can, yeah. So here's an image of like the ship and the station, the Palma station, a view from the top deck where you can see the ship, and then you see ice is just all over the place. And of course, you know, like, well, you don't really need a fridge if you're in Antarctica. As you can see, they have soda cans. We just scooped some ice with the tipper, and then, yeah, you just have your fridge out there. So my current research has been mostly, these days, it's on remote sensing of plastic litter. So that is remote sensing from ships, drones, aircrafts. There are new instruments which are upcoming. They are called high altitude pseudo satellites. So you find them at a height or altitude that is just above aeroplanes, or like where aeroplanes can fly, and just below where satellites and CubeSats. So CubeSats are small, like 30 centimeter sized satellites. And then, of course, you have fixed stations on land, and then also like small boats where people can do surveys of plastic. So here on the sea surface, you can see the different, just an impression of like plastic litter on the sea surface, and also leaving the rivers on land. So it's trying to find sustainable and innovative remote sensing technologies. So for the developing nations, you need something that is affordable, and you can always keep on doing the research over the next coming years. A bit about the university where I am currently stationed at. So it was started in 1973. Oh, I don't know how this. Okay, so it started in 1973 as a teaching education university, and then in the coming year, like in 1974, that's when other degree courses were established. And from the statistics from last year, it's quite a big university, about 15,899 students, about 250 professors, then of course about 1,316 scientists, and then technicians and other supporting staff, that's about 1,247. And at the moment, we have about 95 study courses, and strong mostly in educational science, energy and nanosciences, hearing physics. So here you see we have one of the best like institute dealing with hearing science. And then, of course, interdisciplinary marine sciences, which is the aspect I am dealing in. And then, of course, from the main university, we have the Institute for Chemistry and Biology of the Marine Environment, ICBM. So for some people, they tend to think ICBM is intercontinental ballistic missiles, which is, yeah, it's a strange shortcut or abbreviation, but yeah, okay. So we are, if you look at the map, or whenever you get a chance, if you go on Google, Germany is, well, I would say in the middle of Europe. On the left, you have Belgium and Netherlands somewhere here, and then you have France down there. Then you also have Switzerland, Austria, and then Czech Republic. You have I forgot the other countries. I should know this. But then, of course, when you look at my institute, we are based on the north. So here is Bremen, Oldenburg. So here you have Bremen, you have Hamburg here, and then you have Wilhelmshaven, which is way up northwest Germany. And for the institute, we have the main institute is based in Oldenburg, which is here. And then where I am stationed is in Wilhelmshaven at the station here in the corner here. And then we have also like a small institute or like facilities on an island. So you have barrier islands just covering Germany from the North Sea to the, so here you have the Wadden Sea. So what is the ICBM really doing? It's mostly interdisciplinary research, and most of the scientists, they do research in global oceans, in fjords, seas, lakes, and estuarine systems. And the focus is on marine biogeochemical cycles and energy fluxes in the water and sediments at the boundary between habitats and water masses, as well as functional role of marine biodiversity. So here, if you look at the pictures, they try to capture what we are really doing. So open ocean, you have the microbiology studies, you have the open ocean studies, you have near shore studies, and then you have people doing studies also in wetlands, trying to understand groundwater processes, and then you have ice here. So any questions, or I can proceed? No questions as yet? Everyone is understanding? I'll take a minute, maybe there are some questions. No questions? Okay. No? Okay. So what kind of education is covered at the ICBM? As part of the university, they offer a bachelor's degree in environmental sciences, and then master's degree in marine environmental sciences, microbiology, environmental modeling, marine sensors, and then of course the PhD program is the one I did, which is environmental sciences and biodiversity. And then of course we also have summer schools and then public outreach. So here are some students like doing research on the on this beach. And then you have like small boat facilities where sometimes with this boat you can leave it due to the tides. So we have tides every 6 hours. The water is either going into towards the land, or it's moving towards the sea. So you can also do studies on exposed land. And well, there's some teaching. That's my supervisor here. I think I have one picture of him. And then of course here, just presenting on what the institute is doing research at different occasions. So when we are doing coastal research, the institute where I'm working at CBM, we actually have 3 small boats, and one is Otsum, we have Navicula, we have Zephyr, and well, the biggest one is Otsum, where you can have, yeah, that's always a good question, how many people you can have on that boat. I would say you can have at least 15 people. And well, there are no sleeping facilities, but you can do research on a daily basis, and then yeah, have to find somewhere, a port to station. And then same thing with the Navicula, you can have 10 persons, or you have 5 people and equipment which is at least 400 kilos. And for Navicula, it's 6.5 meters long, and then like it's wide about 2.5 meters. And then of course you see it's half the size of Otsum, so of course you have more people and more weight you can carry on the Otsum. And then similar to the Navicula, you also have the Zephyr, which is slightly longer, but more or less the same class with the Navicula. So that's for the coastal research. Well, because like with these size of ships, it will be quite risky to be going out in the open ocean, because if you have very like high waves, then it will be quite dangerous, and it's not really safe. But then with this one, you can go out to the Wadden Sea, but going out into the open ocean, North Sea, that would be, as I mentioned, it's quite risky. Then of course, if you really want to go out into the open ocean, Pacific Ocean, Indian Ocean, we have the latest, which is pretty, it's quite big, 116 meters length, about 20 meters wide. And so the host institute where, like it's stationed whenever it's back in Germany is at our university, and it's called the Sonne. So Sonne in German, it's the sun. So it's our sun. So it's a very big research vessel. You can have 40 scientists, and each scientist has his or her own room where you have your own bathroom, you have your own bed, a small desk, and a small TV. Also, you have at least 35 crew members, so they're working 24/7, like they are working, and you cannot be out at sea for 50 days. So you can imagine, like, that's at least 2 months. You can be out at sea without needing fuel or anything. The food you carry, you get your meals, you get your breakfast, lunch, and dinner there, and yeah, everything is provided. It's available. You have fresh water. You can, yeah. So on the ship as well, one interesting thing, they how do you say, process the water. You can get fresh water. Yeah, we do recycling of water. So that's, yeah. Yeah, just to give you another impression of the ship, here is an example. This was in Mexico, where it was docked. And you can see here in front, that's where you see the zone, so that's representing the sun. And in terms of size, you can tell, like, from the small boats and that ship. And also it's only for science, again, nothing else, just science. So going down now from university, the institute, now the working group, where, you know, like, for each working group, there's a professor leading the group. So in our group, we are the Marine Sensor Systems Group, and it is headed by Professor Dr. Zielinski. And the main goals of the team are to design, like, autonomous, automated, innovative, and affordable sensors. So the idea is to design sensors or tools that are not expensive. Yeah, but it's always difficult. What is expensive? Yeah, but try to build instruments that are cheap, relatively cheap, and easy to use, so that, you know, like, you turn it on, you collect your data, you don't have to worry about the instrument. And here are just some examples of the instruments or tools we have in the lab. And we have worked, you know, like, on different platforms. So we take measurements from inside the water column. We have fixed stations. We have the boats I was showing you before, different other ships that belong to the German, like, research community. And then here is an example of artificial islands, trying to study how the biology changes when you have, like, these small islands. You change different parameters of the environment. And all these studies have been done in global oceans, fjords, seas, and estuarine systems. So one quick question, anyone knows what a fjord is? I'll give you a minute, maybe they'll type. Do you know what a fjord is? This, F-J-O-R-D-S. So, anyone? No answers? Anyway, you can Google it later. So, yeah. So these are areas where you have ice on top of water, and you have a valley. But you can Google that and try to find out. Anyway, so what are we measuring? Oceanographic properties, salinity, temperature. These are standard oceanographic properties we measure. Like, if you do oceanography, if you're looking at water, these are parameters you measure. These have been measured over the years, over decades and decades. So salinity and temperature, these are tracers. They can help you trace where the water is coming from. And then you have ocean color, plastic litter. Here's an example of, like, an instrument that was designed by one of my colleagues. You can take images of different small microorganisms. Here you can see different examples of the microorganisms. And then we also measure acoustics, sound, and then nutrients. So if you are interested, here's the link to our website. I'll just leave it for a few seconds. Then you can have a look at the website and the different activities. Okay. So, now to the specific, very hard or simple questions, I guess. Why do we need environmental measurements? Well, the main thing is for us to understand the whole reason of doing science, or the ocean is, like, it covers at least 70% of the planet Earth. So we have to understand what's going on and what processes are happening, what changes happening. So, combining theory and field measurements in numerical models, we can mitigate challenges related to each method when used separately. So we have quantitative analysis, where we collect data, And then we use that data to do numerical models to study, maybe, you know, like with numerical models, you can try to understand what happened before or what might happen in the future. So here, like if you look at the arrows, they are all linked to each other, where you have theory, where you know, like you have theory, but then you need data to combine what you assume is correct or not in theory. And then you do the practice of collecting the data, you put that into models, you have an understanding of what exactly is happening. So for example, what will happen in the future? We will sea level rise, why? Will temperature rise, why? So how do you, like for example, how do you answer these questions? You need data. Like for us, we look at ice, you see the ice is melting, you can measure the size of the ice sheets, and then you combine that information with theory, you have numerical models to understand what exactly will happen and when it will happen, right? So you can now make predictions to see, well, we have climate change, sea level is going to rise, temperature is going to rise maybe by 1 degree or 2 degrees. So if it will rise by 2 degrees, what would that mean? Like, is that going to change how we live, or people have to move? Or these are questions, you know, like you have to consider when you're doing environmental measurements. That's where numerical models come into play. They help us understand what the data we collect and what theory is saying, right? Any questions about that? No questions? People are understanding? Well, that's very good. Thank you. Yeah, so I have a 2-minute quiz, and it would be nice if people, I'll give you 2 minutes or maybe 5 minutes, I don't know. You can type your answers. Maybe if you can answer, like, can someone provide examples of these parameters, like ocean properties? What could be an example of chemical, biological, optical, geological, or physical property of the ocean? So maybe, yeah, 2 minutes. We hope people can answer. Just type your answer and then we'll see if, yeah. Are people typing? Okay. Any more answers? 2 minutes, we have time, please. Yeah, more answers? Yeah. Very good answers. Please, more answers. We have very smart people here. More answers, please. I think 1 more minute. Interesting and good answers. But no one has said anything about the geological properties. Ah, there we go. Okay, very good. Very good. Okay, so ready for the answers? These are just examples, not the final answers, but anyway. So ocean properties, when we, yeah. Ah, yeah, okay. So we had carbonates, CO2 measurements, coastal erosion, we have chemical, metals, temperature, density, phytoplankton measurements, transparency, temperature, conductivity, optical densities, color, salinity, heat. Very good answers. Chlorophyll A, volcanic eruption. So, very good answers. I think some of the answers you gave, you can see they are also in the list I have. So this is not like a very big list, it's just a few examples. So for chemical properties, you have nutrients like for oxygen, carbon, sulfates, nitrates, phosphates, iron, like toxic chemicals, and pH, right? Power of hydrogen. So if water is acidic or alkalinic, yeah. And then you have biological properties, you have fish, you have the algae, you have the phytoplankton, you have zooplankton, you have measurements of productivity, you have corals, you have egg counts if you're looking at fish. So for optical properties, you have water color, you have turbidity, you have circuit disk depth, light measurements, clarity, transparency. I saw someone also indicated transparency. And then for geological properties, you have rock types, shapes, size, sediments, clay, silt, granite. These are just examples. And then for physical properties, these are salinity, temperature, density, conductivity, specific heat capacity, sea surface height. Any questions about this, or that's clear? Everyone okay with the examples? Or they want to add another example I might have missed? Huh? There's a question? Hello? Yes, I can hear. Yes. The question is always if you have the time and you have the people. Does that answer your question? Yes, of course. Let's see if I don't have any picture inside. So just to give an impression, where it says science, you have labs under there. You have also labs just on top. So there's enough space. Okay. Okay. Okay, so we continue. Well, so we are talking about going out at sea. One thing that might not be obvious, or maybe it's obvious, but there is a lot of work that goes into planning. Well, of course, you have to find the money, you get the money, but you have to do so much planning. There is planning. What does that mean? Who, what, where, when, why, and how. What are you going to collect? Like if you're a group, what do you want to study, right? If you're going to look at lakes, you want to look at certain parameters. You maybe just want to get water samples. You want to collect like fish samples to see if maybe they are eating plastics. But then if you're going out in the open ocean, you might also in lakes, you might want to collect sediments. But if you're going to be in the North Pole or South Pole, you want to collect ice core samples, or you also want to collect sediments. And the other question is always where? Where are you going to do the science? If we are looking at the ocean, then of course the ocean, or like water bodies, you look at lakes or rivers, or you want to do it on land, right? And then how, of course, you have the ships. If you're going to be dealing with science on water, you can use ships, and then of course aircrafts as well. You can get observations, or you can use satellites, right? And one of the most important things that you have to do is to address why you're doing it. Why do you want it? Yeah, of course, you can do science because the money is there, but you have to answer something relevant. How is that going to push science for want to develop something or to study something that will improve what we already know. Like, yeah, if we know that in the lake there is an algal bloom, then yeah, but why do we care? You know, like the question you always have to ask yourself when planning is, if someone is going to say, so what? Yeah, you want to study the Lake Victoria, but then the question is always, so what? You have to have an answer for that, right? And then, of course, you have the question of who. You have citizens. Citizens can help you do science. You can have scientists, students, technicians, and ship crew. And when you have to plan the dates, the time and year you want to do things. Maybe you want to do a seasonal study. You want to see what is happening in summer. Is it the same that is happening in winter? Like if you have a region where you have different seasons. So again, planning, that's a lot of work. But over years, of course, if you do the science over years, you have the experience, and the planning becomes very, like you can do it in your sleep. But of course, you have to prepare. Here, just an example. Like before you go out at sea, you need a map, right? You need to know where you're going. You need to have. So in most of the cruises I've been on, it takes time. Before you even apply for the funding, you have to say we are going to these locations. We are going to do this from this date to that date. And when you're also on the ship, you have to prepare a daily plan. Like today at around 9 o'clock, we are going to be at this station. We collect these samples. So when you're collecting samples on a big ship, the most important thing is one thing is happening at a time. You cannot have someone doing something else on the side and someone, because if there's an accident, then that becomes a problem. So the rules are always one thing at a time. So you see, for this cruise, we went to Antarctica. You start with taking like trace metal like measurements. After that, you take a mockness nest. I'll show you an example of a mockness nest. After that, you do like optical cast. Then you do a CTD. Then you do 2 meter zooplankton net, 1 meter, and then you recover a mooring. Like one thing at a time, and it's a specific time. Like it might take as long as possible, but it doesn't matter. You start around 9 o'clock, you do your measurements. When it's finished, you go to the next day. So here you see day 1, 10 January 2016. Day 2, same thing. You have a list of activities, and they have to be done in that order. In some cases, yeah, things can change if there's a problem, like with an instrument. Okay, so we'll proceed. We were talking about planning, who, what, where, when, why, and how. Here I was trying to give you an impression of what you have to do before you go out at sea. You have to plan the map. You have your fixed stations. So LTER stands for long-term ecological research, and they're like for this study, they have been collecting data, I think, for the last decade or even longer. And what they call process stations, you stay there for almost a day. But then standard stations, you just go there, you take your measurements, you leave. Like maybe 1 hour, 2 hours, you take your samples, then you leave. But the green stations, that's where you stay for overnight. You take certain measurements, you have a time series of the day. And then, of course, you have a daily plan of activities, what you're going to do on that day, as I was explaining. At all times, you only do one activity at a time. No running synchronous activities, because if anything happens, it's easier to manage compared to when several things are happening at the same time. Sometimes you lose instruments, and then that means they sometimes have to shut down the ship. In the open ocean, there's no body or where you can apply for permission to do science. So once you're in the open ocean, you can do whatever science you want. Reasonable. Okay, let me put it this way. It has to be reasonable science, as long as it doesn't go against general rules of different countries. So you can do whatever reasonable science you want in the open ocean. You don't have to apply for diplomatic permission to to do science in those waters. So, for example, if I'm going to be doing science in the South African, say, well, you can't do what you want to do here in our waters, or you have to apply for a permit, and these might take maybe a month, and you don't have such time, you simply move away from their waters and go into the open ocean. Yeah, that should be no problem. Any more questions, or is that clear? No questions? Okay. So, we have also instruments that help us maybe, how do I say, nowcast and forecast possible earthquakes, right? So these are, how do we call them, speakers of the ocean. We can put seismic sensors to measure any seismic activity that might happen in the ocean. So there are locations, they are strategically located in some areas where you always get data, and you can at least warn people if things are going to be changing or going to be dangerous. So here's an example. You have a control vehicle, data recording package, zone leading package, acoustic transponders, and then, yeah. Any questions about this? Okay. There's a question. There's a question? No question. Okay. So someone was speaking. Yeah, please. Yeah, hello? Yes. Yeah, so that's a good question. And if you, let's see if I can go back. So this whole data is centralized. If you search Argo floats, you'll see the data is centralized. And in terms of processing data and analyzing data, the one thing people do is they either have, a round robin, or you have workshops where you have scientists from different countries and come together. But in most cases, people use the data for different needs. So that's always the biggest challenge of combining science with different countries, because there's also the issue of funding. Like if you're not funded to do the work, maybe you have a PhD student working on it and that's it. So it's one of those big challenges where if you look at the numbers, right, the USA have over 2,000 instruments, so they have dedicated so much effort, so obviously there's more funding for Argo floats compared to if you look to a country like, Kenya, they have one. And if you're going to have a meeting, obviously you have more people from the USA or like countries where they have more sensors, because, they have dedicated the funding and resources to that. Does that make sense? It's a tough question to answer. No, like there are workshops where they try to combine international, to do international collaboration, but at the end of the day, it's always very difficult, because with science, it's always about funding. If you're not funded, you're funded to do the work for 1 year, and then your funding runs out, then you have to dedicate your time to other activities. Of course, I know it's important to be combining forces, but it's not as easy as we would hope for it to be. Any more questions, or does that help answer your question or help you understand a bit more? Hello? Ah, okay. Right. So on the map Africa, let's see. There are some, like there are some floats running around Africa. Well, not as close as you'd want them to be, but there are some floats around Africa. You see, like South Africa, Namibia, you have some here around the equator, and then you have also in the Mediterranean Sea, like North Africa. And then also you have here some measurements along Mauritius and all the other parts here, Eastern Africa. So when it comes to oceanographic studies, most work has been done by South Africans, Namibians. They do some oceanic studies, and of course, let's see, Kenya some, but mostly South Africa and Namibia, and a bit in Botswana. And then you have in North Africa, not really as far as I know, but yeah. Does that answer your question? I hope so. Okay. Okay. So here's also another example of a glider. One of the instruments is just also program it. You tell it where to go, collect data, most cases salinity or temperature, or salinity and temperature. In the nearshore areas, this is also important, tide gauge, because sometimes if you have ships, there's a question. So yeah, on the map, if you look closely, they don't belong to African countries. I think Kenya is one of the only countries, and South Africa, I don't know if they have. I would have to check the latest map, but you have Mauritius, Kenya, they have some floats as well. Okay, so tide gauge, how oceanographic studies help landlocked countries? Studying the ocean, understanding the dynamics happening in the ocean and how they interact with the atmosphere, like how they control meteorological conditions. So if a storm is coming, then, like if we know what is likely happening, that's how, like how they would help. So it's through hindcast and forecasting information. If you're going to have sea level rise, that is also important information for landlocked countries. Then, like they can warn people to move to higher land. In some Asian countries, strangely enough, there are elephants. They can sense that there's a storm coming, and you see them moving up to higher lands, moving away from the lowlands. And in some cases, they've shown studies where they have good sensing information related to what's happening in the ocean when a storm or hurricane is coming from the ocean and then it's moving towards land, or in some, especially in those small islands, scattered islands. So what happens in the ocean affects us on land. Yeah. Exactly. So that's exactly what's happening in the ocean, or what's happening to the countries that have a seaside is also going to affect us. Because if there's flooding, then people have to move inland, right? So that means there's migration of people. That's a good way to put it. Thank you. All right, so a tide gauge. Another question. That's good. Yes. So these techniques, you see, all the techniques that can be used in the ocean, they can also be used on lakes, but on a smaller scale, right? It just depends how, if you have a large lake, like Lake Victoria, of course, you can also have all these different instrumentation. It's one challenge is always if you have the resources, right? But over time, like with more data coming in, the policymakers will understand like you need to put resources towards studying these parameters, making, like the more data we collect, the more we understand of the environment. So we can do hindcasting. You remember what we talked about? Nowcasting, where we can say, whoa, this is happening in Lake Victoria. We have, let's say, temperature is rising in Lake Victoria. We can have instruments that are providing data in real time, or we can also try to understand what has been happening before. If we collect data in specific locations, and then we have, like a grid where, we are collecting data in these areas, or in the future, also to predict, like, well, we are predicting that next year Lake Victoria will be very cold or very warm, like all these parameters like salinity or temperature is going to change because maybe there's increase in like different chemicals being dumped into the lake. Such questions can be answered through making these observations. I hope that answers the question. Okay. So tide gauge, it tells you how high the water is from, the water is changing. So as I was saying at the station, I was showing like the University of Orenburg as a measuring station where the tide is changing every 6 hours. So the water is either going towards the North Sea or it's coming towards the land. So you have more or less like high tide and low tide, right? So for shipping industries, it is very important information knowing how high the water is, because if they come at the wrong time, they will be stuck. So if you notice in some areas in the world, they either lock the water, like the ports, where a ship gets in, they get water in, and then they get water out, and then they maintain the water level, right? So this is also very important, knowing the tide level. Let's see, next slide. You remember I was showing a plankton net? So there's one called mock nest. This is a multi-open and closing net. Well, yeah, it's a simple way to say it, multiple open and closing net. So what you simply do is you don't want to collect your water, like your microorganism samples from the whole water column, because you don't know what's happening at 50 meters, at 100 meters. So what you simply do, you would have, let's say, a set of 5 nets, right? So with the 5 nets, you can collect water, or like you can collect the sample of microorganisms or material at different depth. So what you do is you go, let's say, 200 meters, you open one net, you collect your water sample, then you go up maybe to 150, you do the same. Then at the end, your 5 nets will have different samples. So looking like this. So in the different nets, they have different collectors here. That's when you get your samples, and then you can identify the different organisms or microorganisms within the different water depth where you collected samples. Make sense? Any questions about that? Okay. So other instrument, if you want to study the magnetic properties of the ocean, you can use a magnetometer. And here's an example of how it looks like the data. So bathymetry, like bathymetry, here you have high elevated land within the basin. So this experiment was done in the West Galapagos Islands. And here you have the measured magnetic field. And here you have the calculated magnetization. So if you are interested in measuring the magnetic field in the ocean. Here also, if you want to do ocean bottom seismometer, if you want to measure underwater earthquakes, you can have an ocean bottom seismometer. Here's an example of like that type of sensor. Here, just another impression of like underwater vehicles. So this is Alvin, which they had 3 people inside, and they went diving about 4.5 kilometers below the water surface. And well, in 1977, that's when they discovered the first hydrothermal vents. And yeah, I think that's it for today. Any more questions or comments? No questions? Everyone happy? Okay. Thank you. Yeah? I can stop? Sorry? Yeah, I'm waiting for no questions. People are happy. So, goodbye. See you tomorrow then.